Okay, so I've titled my talk Rules and Responsibilities. These are the ties that bind us. It's a quote from Neil Gaiman from his novel The Sandman, 1989. Now, the ambiguity in that title is intentional in the sense that when we talk about ties that bind us, what do we mean? Do we mean that the rules and responsibilities keep us constrained as to what we can actually do? Or do those rules and responsibilities provide us a means of actually interchanging information, a means of communication between ourselves that we can actually understand each other based on common ground? And I'm going to try to explore that little issue in a little bit more depth in the next few minutes. Now, let's try and simplify things. Let's concentrate on the two types of rules that really interest us most. And those are perhaps predictive rules, and on the other side, restrictive rules. And the way I've defined those is, first of all, the predictive rules help us understand the system we're dealing with. So things like the law of diminishing returns, law of supply and demand. If we're in the business world, let's say. If we're in the physics world, we might be talking about Newton's laws of motion or Faraday's laws of induction. The restrictive rules, on the other hand, help us govern or regulate the system we're trying to deal with. And with a matter of contention here that I'll try and address a little bit later, perhaps to ensure fairness or safety when we start to interact with the technology and the technology starts to interact with society. So we might be talking about various EU Commission regulations, federal aviation regulations, or a pile of other documentation of much the same ilk. Okay, so I'm going to talk about the tension between predictive rules and restrictive rules in a little bit more detail. Now, predictive rules, let's talk about those in a little bit more detail first of all. And I'm sure you'll all agree with me, especially after you've seen this slide, that not all are created equal. So on the left-hand side there we have the rule of the Gartner height curve, this idea that a technology first achieves a tremendous amount of first player buy-in, then everybody gets upset with the technology, deserts it, and then slowly that technology creeps back into some form of public acceptance. Now, that's not a firm rule on the basis of the one on the right, of course, in that some technologies obey that trend, some other technologies don't. Now, dmv by dt equals f. It's a fancy way of writing force equals mass times acceleration, of course. And that rather grim picture of Isaac Newton there is to remind us that this law is a fundamental rule which governs how the universe works. To the extent that if we're talking about aircraft type velocities, let's say velocities of 10 to 100 meters a second, and with eVTOL we're sitting much more down near the 10 than the 100, then this law is correct to one part in a million billion. That's one with 15 zeros sitting after it. So in other words, if your predictions are not consistent with Newton's laws, there's no question about it, there's no argument. You are wrong. It's not like if your product doesn't conform to Gartner's height curve. It's a very different kettle of fish. Now, that has consequences, both positive and negative, and hopefully you'll see a few of those in the slides that I'll present. So Newton's laws underpin effectively our understanding of the real-world physical behavior of the kind of aircraft that we're interested in. So the equation at the top and the equation at the bottom, you can see all these equations are very similar form. I've written them in a fashion which actually exposes that we're looking at almost the same thing here. The equation at the top and the equation at the bottom govern the flight dynamics of the vehicle, how it moves through the air in response to the forces and moments. That second equation there is the one that I've devoted most of my career to studying. It's the Navier-Stokes equations, which govern how the aerodynamics of these vehicles operates. Okay, so let me concentrate a little bit on where my strengths are, and let's talk about the Navier-Stokes equations a little bit. First of all, here's an index application, which kind of has a bit of a lead-in. It kind of says that if your aircraft's going to generate a force, then it's going to generate a downwards velocity in the air. And that's shown in the diagram at left there. Force upwards requires a downwards velocity, which we call the downwash below the aircraft. Now, if I take the downwashes that are produced by various aircraft of various types and I map them onto this neat little diagram over here, where we have, I wonder if this will actually work. Yes, wow. You can see that helicopters are all clustered down here, tilt wings are all clustered up here, and eVTOLs are off on their own tangent, if you like, out to the left of the diagram over there. So from that particular diagram, you should see that it's clearly obvious that eVTOL aircraft are different to what we are used to. And that's the first point that I think we need to take home. So when Simon asks whether we can apply the kinds of technologies and understanding that we've developed within the helicopter industry, I would say, yes, that's a very worthy ambition, but to what extent can we actually do that? Where should we be careful? Where should we kind of step back and say, hey, is this actually the same situation as we've encountered within the helicopter industry before? So how significant are these differences? Is it just a matter of saying, well, these differences are trivial and we don't need to consider them, or do we have to be a little bit more careful about what we do? So we can make deeper predictions. We can actually use the Navier-Stokes equations, and we can come up with various inferences. We can say, for example, that if we take this diagram over here and we plot, oh, yes, there it is, vertical speed over here, rate of descent, if you like, versus forward speed, then there's part of that flight envelope in which the aircraft will be prone to a potentially catastrophic collapse of its aerodynamics, also known as the vortex ring state. Robin and Ryan talked a little bit about that in the questions after Ryan's talk. And this element, this area, is a polluted area. You can't actually go into that with your aircraft. Now, the consequences there for eVTOL aircraft is that rapid descents at high velocity and steep rapid descents are not possible, whereas helicopters can actually do that. Is that a showstopper? Talk to Ryan and he would say no. All you do is you adjust the trajectories to accommodate that. Is that the issue, or is there something more fundamental in that vein? Now, so what I'm going to do is I'm going to tell you a little bit of a story. Where, okay, first of all, let's just hold our horses a little bit. In that I can stand up here and I can be very, very pontificational about the applicability of Newton's laws. But having simply invoked the underlying physical principles actually means very little in practice. Just because I say that I've solved the Navier-Stokes equations doesn't actually mean that I have. There's a good implementation matters, and this is a real bone of contention within industry. A major problem in this field is the quality of the tools that we use to analyze these very, very complex aerodynamic issues which take place in these vehicles. So out of the box generally isn't good enough. So if you have an industrial quality simulation of vortex ring states, such as the one that I've shown over here, that's not necessarily the same as a research quality simulation of vortex ring state, which will tell you actually what's going on within the system. So it is possible to make bad predictions. And of course, this cuts both ways. If you make a bad prediction, you can either say that the system is going to be more susceptible to these kind of problems than it actually turns out to be in reality, or you can, of course, go and say, my model predicted absolutely benign behavior, and there's no problem here. So where does the truth actually lie between the benign and the horrendous? And that's a very difficult question sometimes to address. Okay, so back to restrictive rules. These help us govern or regulate the system that we're dealing with. In other words, to ensure fairness or safety, as I described earlier. And the issue is, can these actually come into conflict with our predictive rules? And a short case study will illustrate the complexity of what we're trying to do today. So if we go back to 2022, this was a way that EASA imagined that eVTOL aircraft would operate within a dense urban environment. So there's lots of buildings about. What you do is you'd effectively keep the aircraft above a certain level, and you'd punch down these holes towards vertiports into which the aircraft would have to descend and come to rest. Okay, sounds very simple in practice, sounds very practical, until you start to envisage what happens to an aircraft when it punches down into one of these holes. This is the region of the envelope subject to vortex ring state, and you can actually map these trajectories of the aircraft coming into one of these holes, if you like, onto that particular envelope. And if I focus in over here, you can see something very, very interesting happens, in that the only part of that envelope that you can actually use once you've defined a hole with certain geometry is this green patch over here. But what that green, and then you have to descend from this point over here, which maps to there, down to 0 feet per minute and zero descent rate and forward speed, in other words, landing, via a trajectory which will look something like that piece of curve over there. But you can see in that situation, you're forced to contend with VRS. There's no ways that VRS doesn't become an issue. You descend too slowly, that's not good for batteries. You descend too fast, you're going to into VRS if you're sitting in that green area. There's no doubt about it. Okay, so how do you get around that? Well, you don't design vertiport infrastructure in that particular sense. You can see what's happening here is that the regulators are actually regulating the industry out of business. There is no way, potentially, that the industry can actually cope with regulations which are defined at that particular level, and with that lack of insight, if you like, into how the aircraft can actually operate in principle. So Newton sits there and shakes his head and says, what do I do? I can't help you in that particular circumstance. Another issue, of course, is that when you get to low altitudes, you start to interact with the ground. And the longer you stay at low altitude, descending slowly, the stronger that interaction with the ground happens to be. So there's this problem that if you don't incorporate that level of physics, then perhaps faulty design of vertiports risk coupling the two problems together, and you end up in an even more severe problem than you might imagine. Now, aerodynamic effects during vertiport operations actually poses a real problem, and actually the problem is threefold. First of all, if we have overly dense operations, then there's interaction with other aircraft, the kind of wake turbulence issue that you might consider with coming into Heathrow, stacked behind a bunch of other aircraft with a 757, let's say, in the mix, which will cause you extra trouble. Maybe a Joby or maybe a Vertical or maybe an Archer is going to be an aircraft like that. We just don't know enough about that particular physics at the moment. When you come to the issue of approaching your landing site, downwash then becomes an issue. The stream of air downwards below the aircraft, which is inevitable, it's got to hit the ground somewhere and got to dissipate. What's it going to do? Is it going to dissipate on top of your Ferrari, which is parked in the parking lot, or is it going to be controlled in a proper manner and deviated to somewhere where it does no harm to the surroundings? Is it going to lift your roof tiles off in the parlance of anybody who lives near Heathrow? Once you get down to the ground, that outwash spreads outwards and causes even more of an issue. Okay, so you can see that there are all these physical issues which might come together to make the integration problem a lot more difficult than merely saying, okay, we're going to park this vertiport over here and we're going to design these aircraft to operate in this particular fashion. But it sounds like I'm being particularly negative. And the issue that perhaps we can most faithfully address is how can the predictive and the restrictive actually complement each other? And here's a perfect example of that. This is work that's been ongoing for 3 years. I've been helping the CAA to do this, to actually try to understand this outwash problem in a generic fashion. So we're not picking on Vertical, we're not picking on Joby, and we're not picking on Archer. What we're doing is we're actually conducting a generic survey of the characteristics of these aircraft to be able to determine up front what the characteristics of these vehicles are going to be when they come into service. And because it's done in such a generic fashion, we actually understand the basic physics. You come to us with a 12-rotor, 6-tailed monster, we can actually run that through our models and actually tell you what the outwash is actually going to be. So the regulators in this case are commissioning basic scientific work to help them understand emerging issues, and we'll hear a bit about that later. And this, of course, is work that the OEMs might be tempted to do and perhaps should be doing for themselves, but won't or can't for whatever reason. And this is where the regulators can step in and be particularly effective. Because the benefit is community-wide. We can expose and head off future safety issues. We can understand where previously there was hubris or hot air. And we can smooth the bumps, in the words of Mike Price, who was mentioned in Ryan's presentation, on the road to innovation and make a life a lot easier for a lot of people just by investing a little bit of time and attention and money up front. Okay, so the idea here is multifold. First of all, our target demographic is a little bit different to that which we've encountered within the helicopter community up to now. Grandmothers, children, dogs, suitcases, the kind of people that you wouldn't expect. Most of the analysis that we have is focused on burly US Marines. So you can see there's a big chunk of work going on here to try to understand how to, in the words of Ryan and Mike, how do you make these people prepared for the kinds of interaction with these vehicles that they're going to experience? And then how do you actually tailor that experience in such a way with where their physiologies are actually able to cope. So a Marine standing waiting to board a Chinook is a very different, I won't say animal, a very different character to a grandmother standing distracted by children trying to get onto an eVTOL aircraft. Another thing, I kind of laughed a little bit out loud when I saw Ryan's movie showing a nonchalant pilot standing right in front of the aircraft and not experiencing any outwash. Because our experience is standing right in front of the aircraft is probably the best place to stand for many of these vehicles. So this is some of our simulations here which show where the true spikes in the outwash pattern happen to be. And it's based on kinds of simulations that I'm showing over here. And you can see that the detailed configuration of the aircraft makes a tremendous difference as to where that particular, those outwash spikes happen to be. And we have the technology. We can do this work up front and we can solve a lot of these problems. So naivety, I think, is a big stumbling block, especially when that naivety is born out of hubris. We don't know everything. And last thing I want to come out of my little presentation here is that we do know everything, because we certainly don't. So the Dunning-Kruger effect, perhaps, is a very good example of a predictive rule which doesn't actually work in practice. Those of us who think we're smart always say that we know less than we do, and those who are not quite so smart always think they know more than they do. But it's not like that, really. That's an obviously debunked predictive rule. But when we start to see pictures like this is hubristic. This is not consistent with Newton's equations. This is fundamentally wrong. You're not going to jump out of your eVTOL and march across and slowly swan off into the sunset on a moonlit picnic, because we know from helicopter experience that's the situation. right? So we need to come to some form of reality. We need to sit in the middle. We need to understand. We need to be honest about some of these problems, because this is our industry. This is what we do. This is what we're proud of. This is what we're going to produce. This is what we're going to inflict on the public in the worst case, and this is what we're going to present to the public on the other side, and actually achieve many of the lofty goals of making urban transport a much nicer prospect than it happens to be at the moment. Now, the real reason why we're here is that siloed thinking poses potentially an even bigger problem than hubris or lack of understanding. That is why we were here. AAM will only become a reality if a broad enough spectrum of expertise is assembled around the table. And when I look around here, this is the broadest spectrum of expertise that I've ever seen at a conference like this. And I'm very happy to see that. So we have people across the spectrum, from town councils to OEMs, with everything in between, which is really great. And so thank you, everybody, for coming along. Hopefully we can find a way of talking and sharing. This is the answer, I think. It's to actually start to address the fundamental issues that all concern us, but perhaps some of us haven't really been very good at talking about. So not everything is commercially sensitive. In fact, a lot of stuff you'll find is being looked at by the guy sitting next door to you in his own silo. So perhaps think about what you can actually share with the industry. So ICAO's trouble in coming to airport regulatory principles is largely a result of not being given data by the OEMs. And that needs to change. The OEMs need to get off their bums, frankly, and actually get with the program. Otherwise, their products are not going to become a reality. Not everything is innovative. History and other disciplines have much to offer. That's de Bottezet's 1917 quadcopter. Nothing's new under the sun, to a certain extent. And the important thing, I think, is to realize that if one of us fails, perhaps I should put a caveat there, spectacularly enough, it's likely we all fail. So let's get together. Let's use opportunities like this to really get to the bottom of the issues and talk them through. So I'm going to leave you here with this little bit of what should we call it? That's a little bit of ambiguity, if you like. In this case, between perhaps gloom and positivity, if you like. On the one side, a negative picture of the industry, and on the other side, a positive part of the industry. And let's move on, and let's see what we have to offer today, and let's get down to business, because we certainly need to.